Well, good afternoon to everyone. I'm Alessandro Papitto from the Astronomical Observatory of Rome, and actually I'm stuck in Rome. I would love to be there, but it wasn't possible. And also, since I had a few connection issues lately, I opted to send a pre-recorded version of this talk, but I'm here and I will be happy to take questions during the Q&A session. Well, in this talk, I will try to show you how millisecond pulses in compact binary systems are ideal systems to study how the interaction between the magnetic field of the neutron star and the inflow of mass provided by a companion star actually determines the emission mechanism powering the pulsar, whether it is accretion or rotation power. As a matter of fact, millisecond pulsars in compact binary systems are coming to flavors. Either they are particle accelerators powered by the rotation of the neutron star magnetic field, and these particles in turn produce a pulsed emission observed from the radio up to the gamma ray energy band, or the neutron star accretes the mass lost by the companion star. This is channeled by the magnetic field of the neutron star to the magnetic poles, and we observe an accretion-powered X-ray pulsed emission. Historically, these two emission mechanisms have been considered to be mutually exclusive, since the presence of high-density plasma in the magnetosphere is expected to turn off the particle acceleration mechanisms that give rise to rotation-powered activity. However, the scope of this talk is to show you that observation of transitional millisecond pulses and lately the discovery of optical and ultraviolet pulsations from millisecond pulses are actually questioning this assumption, suggesting instead that perhaps accretion and rotation power can coexist at least to some extent. Well, we already heard from Sudip earlier in this session that the accretion and rotation power are tightly linked to explain the evolution of millisecond pulsars, since they are the outcome of a long phase of mass accretion that have been spun up in a low mass X-ray binary, and only at the end of the accretion phase they turn on as a rotation-powered millisecond pulsar. However, since, well, more than a decade, I would say, we know that a few millisecond pulses in compact binary systems can show fast transition between rotation and accretion power regime, and they are dubbed transitional millisecond pulses. And here you see the light curve of the pulsar in M28, the globular cluster, that was observed during an accretion outburst, was bright in X-ray, but as the X-ray flux went down, and so did the mass accretion rate, the pulsar was very fast in reactivating as a radio pulsar powered by the rotation of their magnetic field. So showing really how these transitions can happen very fast. Well, this source taught us that it is variation in the mass accretion rate that produced this variability. As a matter of fact, with a high mass inflow rate, the gravity of the neutron star dominates and you observe an accretion-powered X-ray pulsar. On the other hand, as the mass accretion rate goes down, the expansion of the magnetosphere pushes the disk mass away from the system, and at a certain point, a rotation-powered pulsar turns on so that the pulsar wind sweeps away all the remaining matter and the system shines as a radio pulsar. Well, in a gamma ray X-ray luminosity plot, this transition would look like that. In the bottom, you have the rotation power state in which the dominating source of energy is the spin-down power of the pulsar, while in the accretion power state, of course, is the accretion power which is dominant. However, this pulsar of M28 and the other two confirmed transitional millisecond pulsar and all the 4 or 5 strong candidates that we have identified so far are most often found in an intermediate state, which is dubbed subluminous disk state, in which you have an accretion disk, but the luminosity, the X-ray luminosity, is below what is typically observed from X-ray transit, and is indeed comparable to the spin-down luminosity. And as we'll see in a moment, the fact that accretion and spin-down luminosity are comparable is a possible explanation of why these systems in this state show characteristics of both accretion and rotation-powered system. And indeed, this makes studying this enigmatic system very appealing, since it's really the boundary between these two emission regimes. Well, just to summarize, what are the features pertaining both to accretion and rotation power? Of course, we have the presence of an accretion disk, which is proved by the presence of H-alpha double-peaked emission lines in the optical spectrum. We have an X-ray variable emission showing these distinctive transitions between high and low modes. And during the high modes, X-ray pulsations are observed. And also, we have the detection of bright continuum radio emission with properties compatible with the compact jet. Actually, the systems are very bright, similar to black hole binaries. However, no radio pulsations are observed. On the other hand, we have features which are instead typical of rotation-powered neutron stars, such as the fact that they're bright gamma ray sources. Actually, they become brighter during the disk state than during the radio pulsar state, which basically makes them low-mass gamma ray binaries, something really unusually to be observed from an accreting system, such a gamma ray flux. And also, the neutron star keeps spinning down at the value very close to the value observed during the radio pulsar state. So even if a disk forms in this subluminous state, the neutron star keeps spinning down as it were basically isolated. Well, this complex phenomenology, I don't have the time to mention all the characteristics, also the variability observed in the infrared, optical, ultraviolet, but prompted a flurry of models. Most of them, argued that a rotation-powered pulsar was active in the system in spite of the presence of a disk, or that perhaps the neutron star wasn't accreting the mass inflowing in the disk, but was actually propelling it away. A few works had also been made to trying to interpret the mode switches, the high-low mode switches, which are very fast and second timescales, in terms of change of state, perhaps rotation-powered and accretion disk states. However, so far, a single model capable of explaining all the phenomenology of the system, I have to be frank, is still lacking. Well, to further complicate the things, or perhaps contributing to a solution, came the discovery that transitional millisecond pulses can also show optical and ultraviolet pulsations with very peculiar properties, as we'll see in a moment. This discovery was made by the fast optical photometer CFAP2 that my group runs at the 3.6 meter Galileo telescope at the Canary Island of the Italian National Institute for Astrophysics, as an instrument capable of tagging individual optical photons with an accuracy of tens of nanoseconds. And we used it to observe one of these transitional millisecond pulses in the subluminous state, J1023, and we immediately discovered that the optical light curve showed these wonderful pulsations at the neutron star spin period with the shape that you can see here in the inset with 2 peaks per cycle. The pulse amplitude was just 1%, which is relatively low in X-ray astronomy standards. But since we observe, tens of thousands of counts per second with an optical telescope, way more than with an X-ray telescope, the signal was immediately noted and detected. What is most striking about this pulsation is their brightness. As a matter of fact, they contain 0.03% of the spin-down power, which might seem low at first, but actually turns out to be very large and very hard to interpret. As a matter of fact, of course, the system has an accretion disk, shows X-ray pulsation, so the first option to explain such a feature was interpreted in terms of accretion power, accretion onto the neutron star surface. And we attempted to explain them in the same way that it is done for accreting the optical emission for accreting white dwarf, a cyclotron emission in an optically thick regime. The cyclotron energy is in the right ballpark for a 10 to the 8 Gauss neutron star such as this one. But however, the luminosity that you might expect given the spot sizes and the temperature of these systems falls short by, at least a factor 50 in explaining the luminosity that we have observed, which means that either a very strong beaming is required, which is not really suggested by the shape, the broad shape of pulsations, or that accretion models are unlikely to explain what we have observed. Well, of course, the alternative is to invoke a rotation-powered mechanism, and indeed we know at least 5 isolated slower and younger pulsars that show optical pulsations, such as the crab. However, pulsar 1023, stands out compared to them in sense that its ability to convert the spin-down power into optical luminosity is much larger, more than an order of magnitude larger than the crab pulsar, let alone Geminga and the Villa pulse. So to solve the enigma, we try to combine rotation and accretion power scenario and assumed and proposed actually that the system was hosting a rotation-powered pulsar whose pulsar wind was blocked by the accretion disk just beyond the light cylinder, so that it intercepted actually a large value of the energy flowing in the pulsar wind, so explaining the energy observed in the optical and X-ray pulsations. The pulsar wind, of course, in this configuration is expected to deposit a lot of energy into the accretion disk, produce a shock, and accelerate particles, which, since the shock is strongly magnetized at the distance of hundreds of kilometers from the neutron star, is expected to re-radiate its energy through synchrotron emission from the X-ray to the optical band. Actually, since the shape of the pulsar, the electromagnetic field in the pulsar wind close to the light cylinder, is expected to have such an helicoidal shape, this particle acceleration is expected to take place in a spot where energy is quickly re-radiated, so that in the end you would expect this spot to rotate together with the neutron star, producing in our model the optical and X-ray pulsations that we observe. Clearly, this explanation is very intriguing and appealing, since it would give us, for the first time, the opportunity to really trace the configuration of the pulsar wind using the accretion disk basically as a screen located very close to the light cylinder surface. This model would explain a few of the peculiarities of the optical pulsations, such as the fact that they appear and disappear together with the X-ray pulsations only during the high mode. The spectral energy distribution is compatible with a single non-thermal process with a shape similar, compatible with synchrotron emission. And also the shape of the pulsations is very similar, with the optical lagging by roughly hundreds of microseconds the X-ray band, which is exactly the time you expect the synchrotron emission takes longer to emit optical emission rather than X-ray emission. And a paper went out by PhD student Giulia Eliano just a few months ago to show that this lag is really constant over time. Well, to complicate even things further, and likely from another point of view, just after a couple of years, we have detected a new optical case of an optical millisecond pulsar, this time from an accreting millisecond pulsar system, actually from the cornerstone, the prototype of accreting millisecond pulsar XJ1808. The pulsations were observed in the optical and the ultraviolet during an accretion outburst at the beginning and at the end, but we have to say that we have observed this kind of pulsations also during the latest outburst taking place in 2022, even during the main part of the X-ray outburst. So what differentiates XJ1808 from 1023 is that this source is much brighter in X-rays, and we know for sure, we can consider for sure that the X-ray pulsations are due to accretion. So what is producing rather optical and UV? You see there is basically the optical and X-ray pulsation in this case are in anti-phase, which is contrary to what we observe in 1023, but still we have a huge efficiency problem, since XJ1808 is even more efficient than 1023 in using its spin-down power to produce optical pulsation. So again, it really seems that it invokes some sort of rotation-powered model, which in this case should coexist with the accretion onto the polar cap. So really, we might ask ourselves whether these two mechanisms can really coexist at the same time, or perhaps accretion might produce optical pulsations much brighter than expected, for instance, through a maser. Of course, this is something that we are investigating, and we hope to give a solution of the enigma soon. So going to the conclusion, I just leave with some open questions. Clearly, this transitional millisecond pulsar offers a perfect case to study the balancing between accretion and rotation power, but there are yet very large open questions, such as how accretion and ejection couple to yield the astonishing multi-wavelength variability, and in particular, what powers optical and UV pulsations of millisecond pulsar. But certainly, such a discovery is really opening a new pathway to study this pulsar, and we hope to give very nice results soon, in addition to the one I presented. And so thank you very much for the attention.